Hello, I'd like to talk to you today about our focused ion beam milling instrument. It's very similar to a scanning electron microscope in that you have a rastered beam which scans over the surface of the sample to give you high magnification images, but instead of using electrons, it uses gallium ions. Because of that, it generates contrast in a slightly different way than the electron microscope, and it also allows you to have grain structure contrast, and you can also dig cross sections into the sample itself in order to provide in situ cross sectioning and imaging. So let me show you some of the features. This is the normal process for a FIB cross section. It'll start with a flat surface on the sample, which I've just shown the surface of a plating. And why do we want to look at platings? Well, this is an example of a common computer component. And these edge connectors all have to have platings on them so that they don't wear out as they get plugged and unplugged. And while this is a very common occurrence in application, it's also used heavily in automotive connectors and medical devices, whether you have implanted devices that require external power or circuitry on just medical devices that work on the bedside, for instance, monitors and other types of units. And so platings are very important to provide extra protection to surfaces, and so we want to have a tool that can help look at those in addition to being able to look at things like optical coatings and a wide variety of materials, including polymers with fillers and such. So this here is an example of a plating, and we see just a perspective view here. We can see a high mag view of the surface, we see its texture, we see some nodular structure to the plating, and we just want to understand a little bit more about what's going on here. So the first thing you do in the FIB is to protect the surface with a deposit of platinum metal, and this is done inside the chamber by emitting a gas, and this is very much analogous when you do mechanical cross-sectioning and embed the sample in epoxy to protect it during the process. And so we can actually deposit quite a bit of thickness on here, up to several microns if necessary, but typically only a micron. And so now we've protected the sample in a region about 30 microns wide and with a thickness of about a micron of this platinum. And so now we're going to turn up the gallium beam current and do our cross-sectioning. And so we view the sample from top down again, and we define the region we want to remove, and then we proceed to let the computer scan the beam over the region of interest and successively remove material until you have a completed cross-section shown here of that same region. You can tell because of the little X's. So when we tilt this and look at it from sideways, now you can see there's several layers in there beneath the platinum strip that we deposited on the surface of the sample. And so we're going to examine this in greater detail. So what we have here is the substrate is a copper plating in this case, and on top of that there's a nickel deposit, and you can tell based on the grain structure that it's an electrolytic nickel in this case as opposed to an electrolyst type nickel, and that's perfect for this application. And then above that there's a gold plating, which you can see is much thinner than the nickel because gold is expensive, but its grain structure is also fine, which is normally what you see on these types of connectors. A large grain structure gold would be softer and might not be applicable to the application. And then of course we see the platinum we had put on top to protect the surface of the sample. So let's look at a few examples. This is a surface of a clean copper sample with just a little X marked in the middle of it. And this is so that we can see why we get the grain structure contrast that allows us to see these layers so distinctively, whereas in an SEM they would look much more homogeneous and wouldn't have that distinctive grain structure in a standard SEM image. So the ion beam hits the surface of the sample and it channels in between the crystal planes. And so based on the angle each grain in the material is at, the ions can penetrate either more deeply or they don't penetrate as deeply, which affects how bright they appear. So when we take this exact same field of view and tilt it just 10 degrees, the contrast on about half of the grain switches to a very dark color because the angle of the crystal planes in those grains has changed sufficiently that the ion beam doesn't provide the same contrast for those surfaces. And so if we toggle back and forth, you can see the outlines of the grains are all the same. It's just a matter of angle, and that's why we see the grain structure contrast. So This is an example of an aluminum plate which has been stretched out to form a vessel, in this case a soda can, and it has some inclusions inside of it. And you can tell that it's been stretched out during processing because all the grains are very long and thin as opposed to their more normal equiaxed shape. So you can tell the direction in which the sample was stretched, and you can also see that these hard inclusions, which are not able to flow and bend like the rest of the metal, leave voids around them, which could of course lead to failure if you had enough of those in a single location. Another example is cross-sectioning very, very thin layers. Here we have a nickel layer on silicon substrate, and this is a total thickness of less than a half a micron, only a few hundred nanometers. When you have very, very thin layers, they're very difficult to cross-section in the traditional mechanical method, and so using the FIB, in addition to providing the better contrast in some types of materials, also provides a better surface than these other sample prep methods provide. Another feature of the FIB is to be able to target very, very small features. When you have small defects in optical coatings or semiconductor devices, in this case we have a defect that's only about half a micron across, that would be almost impossible to target with a traditional mechanical cross-section. But here in the FIB, you're able to go in and slice right into the middle of it so that you can then identify what the material is by taking it to one of the scanning electron microscopes that have EDS on them. Or you could do OJ analysis on it to figure out what elements are present. And then by seeing where in the stack it shows up, you're able to tell what part of the process gave rise to the defect so that you can then fix your process and make sure that the defects stop occurring. This is an example of a wire bond, and it's the type of wire bond that would be actually inside one of these packages on an electronics component. And so here we have a gold wire bond coming down onto an aluminum metallization pad. The aluminum pad has good intermetallic growth, which means it was bonded well initially, but you can look at the aluminum metallization and see that it's all chewed up because of some sort of corrosive attack. And so, of course, if this corrosive attack continues, then that wire bond will come loose and the device will no longer function properly. And so identifying the nature of the contaminant that caused this etching is critical to making sure that other devices in the lot won't fail in the future. This is a really interesting example. This is a decorative plating, and this is a brass substrate, and it has two different types of nickel layers, and so they have different grain structures in them because they were done in different ways. Now, the lower nickel layer has a coarser grain structure. The upper one has a much finer grain structure. And this is done intentionally during the process in which the platings are put down. And in the SEM, these would look very similar because you don't see grain structure very clearly in the scanning electron microscope. So therefore, the FIB grain structure contrast is greatly improved over what you'd see in the SEM. And so when we go look at a defect region where you could see some waviness on the surface of the sample, you see that that lower layer nucleated in a very bizarre fashion to provide this large nodule of the coarse-grained material before it was overplated with the fine-grained material. And again, this would not have shown up in a standard mechanical section with SEM. You would not have seen the difference in those two nickel layers because their composition is the same, even though it's their grain structure that's different in this case. And furthermore, because of the high polish, you can see there's small little triangular cutouts in the substrate where it looks like the substrate was etched, which probably gives some indication of the chemistry that occurred that led to the formation of this defect in the first place. One of the more popular uses for focused ion beam milling is to prepare TEM samples or STEM samples. And this is where you need to make a sample that's thin enough that electrons can actually pass through it, and that allows you to do much higher magnification imaging than you can do in a standard SEM, and it allows you to do elemental analysis on a much smaller scale than you can do in a normal SEM, where you're typically limited to look at microns. With a STEM thin sample, you can actually look at features a few tens of nanometers across. So to make a cross-section thin sample in the FIB, you basically perform 2 FIB cross-sections, one in each direction around the feature of interest coming from the front and the rear. And then you come in and you undercut that with the same FIB beam. You're able to take that little coupon and pick it up on the end of a probe and free it from the substrate and then attach it to a sample holder, which then would allow you to pass the electron beam through it once you've thinned it down in the appropriate locations, so that the electron beam will now go through the sample where it's very thin in order to give you that increased spatial resolution in a TEM and the much smaller EDS volume in an STEM. You can also create very complex patterns, and this here is of course just showing the company name, but these complex patterns can be created and loaded into the FIB so it can automatically cut out complex shapes used for MEMS devices, which are of course used for all sorts of micromechanical sensors and similar applications. This is an example of a plating defect where the whole surface is expected to be perfectly uniform, but you can see that there is a large chunk. I say large, it's only 20 microns across, which is a third of a human hair, but this crater in the middle looks like the plating has been damaged, and the question is, did this occur before the plating was put down, or was this present in the substrate, or did this happen after the plating was put down? So when we do the cross-section through this in the same way we showed earlier, we can tilt the sample and see very clearly that the actual dimple was present in the substrate initially, and that the platings just wrap right around the defect. And so the defect, while not good to have in the sample, is not terrible because at least the substrate is coated over with the protective platings. And again, we see a very thin layer of gold on top of a nickel layer in this case. And so that gives us our protection, and we can verify that the sample will still function properly. Thank you very much.